we move on to our final talk by Theodoros.
Okay, hi. You can see my screen, right?
Yep. Just if you want to turn on presenter mode for it to see if it behaves fine, because sometimes swapping to
Yeah, no. Is that better? Is that okay?
Yeah.
Okay,
I can see
great.
that. Fantastic.
Okay.
Well,
thank you for having me. Yep. Thank you for having me. It's wonderful. Alex is in Notre Dame and raining. I'm in Athens and it's 40 degrees Celsius. So it's very interesting to see people from all over the world. I don't know what's in Canada, Dimitri's, if it's that hot, but anyway, my talk will be on a non-local nonlinear Schrödinger equation, and it's a work with Dimitris from the University of Athens. And lately, you also are doing some work with Noel Smythe from University of Edinburgh. So the basic summary is that what you're about to see is essentially new solutions, asymptotic as they may be, but certainly solutions of a non-integrable equation in 1 and 2 dimensions, and how we're going to use already known results from the theory of KP, the KDV, and such to construct these solutions and hopefully evolve them numerically and see that everything is consistent with our theory. So the background is that we will be using shallow water wave theory from the KP theory. That is, that we're going to be using the Solitons of the KP and their interactions to construct very interesting, in what I think is very interesting patterns in this equation. So let me tell you what this is. This is the NLS, of course. There's nothing new here. What I have here is, what I'm saying is, look, the NLS, how does it come about? Well, this is, and I have it, as you see, with a Z in the optics context. So this is a propagation, not time. And what this tells us is that the nonlinearity comes from the refractive index of, say, of a fiber or a medium, and that refractive index, of course, in different media can be different, okay, can be expressed differently. What's important here is, of course, the plus or minus sign, which in the optics language is normal, or I should say anomalous or normal dispersion, the plus or minus sign, or in math, it's focusing and defocusing NLS. So if you try to generalize a bit that equation and add different media from fibers, either that's electromagnetics, or I have here plasmas, optical systems, liquid crystals, BECs. I may be forgetting some references, Matteo. I hope you're satisfied with the references. I try to have the first people that ever did these things. If you know anything better, I'm happy to correct this. And if you go to that, say to liquid crystals, then you will need to modify that N in such a way that your equation now is coupled. In what sense? There is no evolution down here. Now I'm switching back to the normal notations. I have T here, and this is the Laplacian, and we'll be using, of course, both geometries, cylindrical and Cartesian geometries. That's not that important for now. And of course, you can see here that the NLS is indeed a limited case of this. If you take D, the parameter D, to be 0, what you get is the NLS. What I have here is the minus sign, okay, the plus and minus sign, which means that I am actually defocusing here. And I need this because I will be constructing my solutions on top of a constant background. And if I have any chance of having stable solutions, then I better make sure that that background is stable. And I'm going to use this the stability for the background. So I'm on the defocusing case. Okay, note that what I won't be able to construct in the focusing case, but then I won't have stability background. As I said, we'll be using both geometries, cylindrical and Cartesian. Okay, and then we will apply whatever we know from the theory of non-integrable systems to construct solutions of this equation. The only solution that I am aware of is a Sesh type, let's just say, but of course it's a Soliton solution of the 1D case. I have seen some other solutions as well, but I'm not, there is not exact or a hierarchy of solutions as you would expect from the NLS. So if you're going to construct, certainly there is no dark soliton in the sense of the NLS for this type of system. So the first goal is, let's see if we can construct a dark soliton for this thing, even asymptotically not exact per se. So this is what's interesting about this equation is that people have tried to see what happens if you study dark solitons, and there's some important results that state that black and gray solitons do exist for this system. They found this variationally, and they interact rather unexpectedly in that they attract each other that repulse. So dark solitons in that system attract each other, and the NLS they repulse. And what's important here is that for the 2D case, there's an effect called the transfer instability, of course, of the NLS, and that system seems to suppress transverse instability of dark solitons. So there has been some work on that system. Well, I shouldn't say some work; it's a lot of work, but there is not exact solitons for that system. So this is what we'll try to do. This is a sketch of our analysis. So we start with the NLS. What we do, we introduce some new scalings, and of course, a perturbation theory will do multiple scales, and we do this in 2 steps. This is an intermediate step, and you can essentially go from non-local NLS directly to the KP system. You can ignore this, but I think it's very interesting to reduce it to the Boussinesq equation first. And let me show you what I mean. So the first thing you do, of course, is you a matter transformation, amplitude and phase. U naught here is the constant background. Okay, so U naught is real here. Everything imaginary is in the phase. U naught is the real background. I have it here as amplitude, but you can ignore that. U naught is real, and everything imaginary can be transferred in the phase. So what we have here is essentially the first order, the constant background solution of this system is this. So this is the continuous wave, this W solution of that system. If you plug that's an exact result. Of course, you plug this in, that solves the system. So what we're trying to do now is construct higher order solutions in the sense of perturbed solutions over on top of that background. Now, with this, I only have here very briefly the dispersion relation for this, and you can see that I will be needing the minus sign I was telling you, because this is now everything is positive on the right-hand side. Okay, D is also positive, of course. So everything is positive, so everything is stable here, and we need this because everything is going to be constructed on that back. And then you do your normal, I shouldn't say normal, your asymptotic expansions. The only difficulty here is, if you will, that you need to find the exact exponents. How do you find these? This is part of the half, or this is series in epsilon, or the multiple scales that change with the root of epsilon. Of course, you can change all this, You can have epsilon here, you can have epsilon squared here, epsilon squared here, epsilon here. Okay, this is the easiest thing that we found that does a job. Then you plug in, you do your magic, or you know your perturbation theory, and then to order epsilon squared, you find a Boussinesq equation of this type, provided that this is a compatibility condition that will arise from the system, the reductions, and you find that C, which is the speed of sound, as we call it in optics sometimes, C is directly related to the background, okay? And you need to introduce now parameter alpha, which is very important. This parameter alpha, that alpha here, is very important in that it can change signs, as you see, okay? If you take note B1, if B is bigger than a quarter or less than a quarter, then A alpha changes its sign. You'll see in a moment why this is important. You further expand your system now, so you're trying to go from the Boussinesq equation now to a simpler equation. Of course, you need to, if you're going to do that, you need to expand some more and introduce further variables. You see now the traveling frames are more distinct here. You see where the velocity is taking its place. And when you do this, eventually, you find that in order for secular terms, the normal theory of multiple scales and asymptotic analysis, you find that secular terms are removed. You don't want secularities, you don't want any growth, provided this is just the two geometries here. That's why I'm skipping a bit. This is cylindrical geometry, it was Cartesian geometry before. And then you find, finally, that in Cartesian geometry, Kp, okay, notice that alpha here, which, as I said, is very important, and that alpha here is also in cylindrical geometry, is also present in cylindrical geometry. Here's what I was telling you, is that when alpha is negative or positive, we call the alpha negative a strong non-locality, the alpha positive a weak non-locality. You'll see in a moment why. Okay, and depending on that alpha, you may get Kp1 or Kp2. So you have you may have different solutions depending on the sign of alpha. Okay, so that's very important. And you can see that even if I go back to 1D, so suppose that I don't have any dependence on that C here, I get, of course, the KDV, and then you immediately see that alpha here is very important, that you get different solutions for the KDV, even for the KDV, 1D KDV. So you have the Kp equations, as I said before. This is us trying to renormalize the equation. So what you had before, we rescale everything just to make it, this is just for beauty, nothing more. And we make everything appear like the normal Kp, the easiest form of the Kp. Now, if you see here, we've introduced the sigma, parameter sigma, which is the sign of that parameter alpha. Well, if you go back to the theory of water waves, you will see that sigma is essentially the surface tension. This goes in the Kp system because of surface tension. This is introduced because of surface tension, okay? And in water waves, you have Kp2 and Kp1, as I say here. So if sigma squared is -1, which is a large surface tension, you get the Kp1. And when you have +1, it's a small, more typical Kp2. You'll see why I say typical in a second. So what is surface tension? Just let me take you, let's remember our high school physics. What's surface tension? Well, it's the tendency of a fluid to acquire the least surface area possible. Okay, so what that does is allow for small insects to have fun with bubbles. Well, this is not a bubble. This is actually filled with water, or they can even walk on water. Okay, but what I found very interesting in the context of KP is that the surface tension plays a very distinct role, which I didn't know. So how can I, if I suppose, so I'm in KP now, okay? I'm in KP. How can I go to a laboratory, to a tank, and construct the solutions I'm about to give you? Or why am I not going to see some of the solutions I'm about to show you in the sea, in the oceans, okay? Remember, the KP is for shallow waters, but why can I not go to any to an appropriate, I should say, pitch and see the waves I'm about to show you? Well, the reason is because if you have water, see the difference between water, and I have mercury here, is the difference between surface tension. What that tells us here, that's the small sketch, to me it's very enlightening. It tells you that water, the molecules of water tend to make friends. They like the molecules of the glass more than they like themselves. So they tend, you see, they form a concave, what they call a concave meniscus. Okay, you see that they tend to stick to glass better than they stick to themselves. However, mercury, which is the large surface tension counterpart here, it tells you that it doesn't like to hang out with glass. It prefers itself. So if you're going to go back to your laboratory and make an experiment with what I'm about to show you, you better have a lot of mercury and play around with mercury and not with water, because you simply won't be able to model large surface tension. I wouldn't suggest that you do it because mercury is very toxic, but if you do, I would be very, very happy to watch it from a distance. So the difference here is that in paper, I can give you some results for both cases, but it's difficult, at least in the ocean, to see different solutions because of the large surface tension of the KP. Now we construct the solutions based exactly on the solutions of the KP. Well, the first thing you do is take the easiest one, which is, of course, the solid of the KP, the line soliton of the KP, which is essentially the soliton of the KdV. Okay, you see there's a total symmetry in Y here, okay? And we're now turning back to the original variables of the system, okay? Everything here, C is this horrible thing here, but everything you see here is in the dimensions of the original equation. So this is my approximate solution for the epsilon, solution to my original non-local equation based on the soliton, on the line soliton of the KP. What you see here is I'm taking this at t equals 0 and evolving it according to the original non-local equation. So what you're seeing here is these are, of course, initial conditions. You're about to see some evolutions. Everything we do now is in small t, small x, small y, which refers back to the original equation, the non-local equation, okay? So epsilon, wherever you see epsilon, x, y, and t, go back to the original system. So these are my initial conditions. What I will be using is the initial conditions here. This is the line solitons of the KP. And these are the ring solitons in the radial case, okay? Notice here that depending on alpha negative or alpha positive, you have a dark, this is a dark, so you have a dip of the constant background, and here you have an anti-dark soliton, which is very unexpected, at least to me, it was very unexpected that if you change the sign of a small parameter, you get a different solution. The same thing holds for the radial case as well. So this is what we did here. We took the line soliton I was telling you. I'm sorry about the Z here. The Z should be T. It's from another paper that was in optics, so I apologize for this. So we took the far left column is the initial conditions, and we evolve them according, say it again, according to the original non-local. Okay, so everything here is evolved in the original equation. There's no perturbations here, okay, other than the initial condition. Nothing else is perturbed. This is numerical evolution of the original equation. So, and you can see this is propagating, and we checked that it propagates with velocity. Remember that c squared was the absolute value of q naught squared. Everything is propagating with correct velocity. And this is a dark soliton, anti-dark, dark, anti-dark ring solitons, okay, which is very fascinating. But there are some other solutions of the KP, which in my opinion, are very interesting. And they come about with interactions. What happened when line solitons interact? So the line solitons I was just telling you about, now we force them to interact. We have them interact. Depending on the interactions you can have different interactions. Here we have what we call an X-type interactions. What I have here is my solution on the left, the one I was just telling you about, and the right is from a paper with by Ablovitz and Baldwin from the ocean. So what you're about to see is one-to-one representations of the solutions we found with the solutions you can find in shallow water. And here's what they call the X-type with short stem. This is the stem. They call this yellow stuff here is called the stem. This is the long stem, and you can see this is ocean. This is light, or my equation, whatever you want to call it, okay? This is an H-type interaction. You see it in the ocean, you see it in light, and a Y-type interaction. And the way they form, I hope this works, is we have them as a movie here. You have two line solitons. These are propagating in real time, okay, the original time. And as soon as they feel each other, you see that they form, the amplitudes change, of course, and they form a Y solid. This propagates as a Y solid. Okay. Again, this is numerical simulation of the original system. Okay. We did the same with ring solitons. I'm not sure if you can, if someone knows, I'll be happy to learn if there are more complicated structures in cylindrical geometry. And what we did here is we took two two ring solitons, one on the inside, okay, a small one on the outside, and we made sure that the velocity of A is bigger than the velocity it expands faster than the outside. Okay, so that's how they interact. You see that one passes through the other, and nothing essentially happens. There is no interaction. Well, no interaction, I should say that. They didn't feel the presence of each other after they interact. And the same holds, of course, for anti-dark solitons. So these are dips of the background. These are on top of the background. Okay, that's the only difference. And then as you have it, of course, you get a bit greedy and say, well, can I do this for coupled system? When you do this for coupled systems, if you go back to the NLS, when you have coupled systems, you can have actually a plethora of solutions. You can have dark, dark, bright, bright, dark, bright solutions. You can have a lot of solutions here. And we wanted to see if we can get the same or more for our systems. And we did. This is in 1+1 again. We did the dark, dark case, and you see top is, they're both evolutions here. we're evolving the system with the initial condition we found asymptotically. And we found an anti-dark pair, okay? And we also find the dark bright for our equation. I think I went too fast, but it's either too early or too late for all of us. So this is the main references. I'm just going to explain you what you saw. You saw these are the optics, the ring solitons in optics we found, and a very good summary of what we did you can find in the last one, the percentage of Royal Society. So with that, I thank you. Sorry, that was too fast, I guess. I'm sorry.
Oh, no, that's fine. Brilliant work. And it sort of gets us back on time almost. So a double win. So are there any questions for Theodoros? Feel free to unmute yourselves or type it in the chat and I'll read it out for you.
No, I shouldn't stop staring. I'm sorry.
No,
but okay, I'll do that.
I have a vague question about the ring structures. So when you're setting up the evolution of these things in general, there's obviously the problem of the R equals 0 singularity, right?
Oh yeah, sure.
Yeah. Do you just subvert that by having the mass start outside of there, or is there like a 3-step regime like in Johnson's paper?
Well, the R equals 0 essentially in our case would be a dot, right? It's a point. So that won't make any physical. So what we did, we started with an initial radius 5 and expanded from that. So that I don't want to mess with that yet. I'm not there. Plus, the other question, what happens when Z is 0 or T is 0? Because the solid of the radial KdV is, or the radial Kp has 1 over T in its solution. So you have to extract that. And what I was giving you is just the ring soliton itself, not the background and how it evolves in space. But we're working on that. It's not easy. It's not easy.
Yeah, it definitely isn't. Because I remember a talk by Davide Promont, who's been doing a lot of vortex reattachments, and you get a similar model out of that. And obviously, where they connect is at 0. So
no.
So it's a nightmare. So I totally appreciate that it's a very tough problem.
Yeah, well, you do the easy first, and then you go the hard stuff.
Yeah. Are there any other questions for Theodoros? If not, thanks again. Fantastic talk.
Hey, thank you. Thank you.
And thanks again to all our speakers for today. A great series of talks. And thanks to the people who have been hosting posters as well. Seeing some really nice work there as well. And so the room is open for free discussion now. So go ahead.